Good day, it's your man Chiefs again. We are continuing with work, energy and power, continuing from the questions that we looked at last time and the background that I gave on work, energy and power. Let's see how best we can remove the cobwebs from our heads by starting off with a question. And this question reads, the graph represents the relationship between work done on an object and the time taken for this work to be done. So there is, on the y-axis, work done, and on the x-axis, you have got time. The question asks, the gradient of the graph represents think of it, what does the gradient show you? The gradient shows the change in y over change in x. In other words, it is showing the work done over change in time. What have we done that gives us such a value of work done over change in time? Think about it. I'm sure you've come up with the answer. The rates at which work is done is power. Excellent. Let's move on to another important factor that I'm introducing, maybe for the first time, maybe not, the aspect of efficiency. Percentage efficiency of machines talks about, because remember when we are talking about power output of machines, they've got a theoretical output that's written on them, and they've got an actual output that we can get after calculation, multiplied by 100, give us the percentage efficiency. Percentage efficiency tells us whether the machine is efficiently working or not. A machine with a higher efficiency means that it's working closer to its theoretical value, which means it works well. So it will have maybe a 92% efficiency. If it has a lower efficiency, it means most of the energy is being lost somewhere within the system. It could be lost through sound, through friction, or through heat. Think about those things as you do or find yourself doing calculations on efficiency. Well, our study guide, written by Timothy Sibeko and Norman Muvoti, which I constantly refer to, has got a lot of questions that can help you master the things that we have been studying for the past few days on energy, power, and work done. Here is a couple of questions that I just picked from the study guide randomly. And I am encouraging you to get hold of that book so that you can learn more on the aspects that you need to know for your exam. So let's look at the few questions quickly. Here is one question that says, the engine of a specific car provides 800 joules per second. The car travels on a freeway at a constant velocity of 20 meters per second. So let's look at the question 1.1. 1.1 says, calculate the force the engine exerts on the car. Right? We can think of it in terms of power. If this engine has got an energy of 800 joules per second, it means that the power outage is 800 watts. The question 1.1 requires us to find the force. We know that power average is equal to force times velocity average. You can do the substitution here and find out what the value of the force is. Let's do it together quickly. The power is 800. The force F is unknown. The average velocity is the constant velocity that we hear of, right? Which, if it wasn't given as a constant velocity to get the average, we will get the two different velocities and divide by the number of the velocities, which are 2. But in this case, we got 20 as our average velocity. Therefore, the force is equal to 800 divided by 20, right? That's simply equal to 40 newtons. Excellent. Let's look at 1.2. It would have gained kinetic energy in the direction of the net force. In this case, it is moving at a constant velocity, right? So therefore, the car does not gain kinetic energy because it is moving at a constant velocity, i.e., acceleration is equal to 0. We can apply that also to work done. In other words, in this instance, we can think of what's happening to the change in kinetic energy within this car. It has no change in kinetic energy. Let's move on to another question. Question number 5, which then says, a car of mass 900 kg is moving at 15 meters per second at a force of 144 newtons acts on the car in the forward direction over a distance of 20 meters. Ignore the effects of friction. Now, if you look at question 5.1, it is asking us in this instance to ignore the effects of friction. If there was friction in this instance, what do you think would happen to the car? The car would reduce its velocity. There will be a decrease in its velocity because of the opposing force of friction. However, in this instance, we are supposed to calculate the kinetic energy of the car before the force is applied. In other words, we want to find the value of EK. What do we know? We know that it is moving at 15 meters per second, but then a force of 144 newtons acts on the car in the forward direction over a distance of 20 meters. Now ignore the effects of friction. Kinetic energy, as we know, is calculated by EK is equal to half of mass multiplied by velocity squared, right? Do we know the mass of this particular vehicle? Yes, we do. It's in kilograms. We don't need to change it. 900 multiplied by its velocity, which is 15, all raised 15 to the power of 2. You can pull out your calculator. I think I got mine right here. Always close to me, my blue baby. It says a half of 900, which is 450, multiplied by 15 to the power of 2. Right? I'm sure you're coming up with an answer that's equivalent to 101,250. And remember, we are talking about energy, and this energy is in joules. There is your answer. Your EK is in joules. Question 5.2. Let's put a division here because we are continuing with that particular question. Question 5.3 says calculate the acceleration of the car over the 20-meter distance. What do we know? We know that there is a force of 144 newtons. If we know the force of 144 newtons and the question is asking us to find the acceleration of the car over that 20-meter distance, we can be able to calculate it by considering that second law of motion states that a force, which is the net force, is equal to mass times by acceleration. Our net force is 144, equal to the mass of 900 multiplied by acceleration. Therefore, 1,4 divided by 9 is equal to, I just divided by 100 for convenience there. 1,44 divided by 9 is equal to 0,16 meters. What am I calculating? Acceleration per second squared. Let's move on to 5.3 quickly. It says calculate the velocity of the car at the end of 20 meters. Now think of it. We've got acceleration equal to 0,16 meters per second squared. We got V initial being equal to 15 meters per second. We also have delta x being equal to 20 meters, right? Using those three, we can actually pick up an equation from the equations of motion that we can use to calculate the value of V final. In other words, V final squared is equal to V initial squared plus acceleration multiplied by 2, okay, multiplied by change in A, Y, or the change in X in this instance, which is the displacement. So our Vf squared is equal to 15 squared plus 2 times acceleration of 0,16 multiplied by 20. Let's do the math quickly. 15 squared plus 2 multiplied by 0.16 multiplied by 20 will give us an answer of, just forgot to put the brackets around 20 there, is going to be equal to 231.4. And remember, this is VF squared. So therefore, V final is equal to the square root of 231.4. Recall answer, square root of that will be equal to 15.21 meters per second. There is our final velocity. So we have applied our knowledge of Newton's second law, our knowledge of equations of motion, applied our knowledge of kinetic energy in this particular question. Now remember, your knowledge is never in isolation. You should know that at this stage you must be thinking like a scientist in order to find out the values or the different answers for the different questions that we are now looking at. Because now we are looking at generally how exams would ask us questions. Look at question number 2 here, okay, which is a trolley of mass 120 kg is released from rest. Now mark released from rest, which means V initial is equal to 0, okay, meters per second, right? At point A, it runs down the track to point B, which is 6 meters lower than point A. If the effects of friction are going to be ignored, the question asks us to calculate the speed of the trolley at point B. So what we need to do is to calculate the speed of the trolley at point B. Now that we are done with this question, let us erase it. You can go back to it by rewinding your video and finding out where you might have missed out on, and in order to understand clearly what this question was all about. Good. Now, let's look at this one here. It says, calculate the speed of the trolley at point B. What is this question really pointing at? This question is pointing at the aspect of mechanical energy, right? We must know that in the absence of friction in this particular motion of the object, right, the mechanical energy is conserved. In other words, mechanical energy at A is equal to mechanical energy at B. What is mechanical energy? Do you remember what mechanical energy is? Go back to your notes and find out if you still remember what mechanical energy is. Write it down. But let's put the formula for mechanical energy at A. Mechanical energy at A is kinetic energy plus potential energy. We are saying the kinetic energy plus potential energy at position A is equal to kinetic energy plus potential energy at point B. Now the formula for kinetic energy at point A is simply given by half mv squared at A. So half mv squared at A plus mgh at A is equal to half mv squared at B plus mgh at B. In other words, when we are substituting the values, half the mass of 120 times initial velocity of 0 squared plus the mass, which is 120 times 9,8 times the height, which is 6 meters, is equal to half mass 120 times the velocity of B, all right, which is what we are looking for, squared, plus m, which is 120, g, 9,8, multiplied by the height, which is 3. Okay, so this is talking about how energy is being conserved. So the energy here is equal to the energy there, and so on and so forth as we go on the ramp, right? So let's move on. This is 0 plus, pull out your calculator, let's calculate together. 120 times 9,8 times by 6 is equivalent to 7,056. Half, that's 60 VB squared plus times 3, that will be divided by 2, 3, 5, 2, 8. Okay, now what does that mean? It means that 60 VB squared is equal to 7056 less 3528. Okay, which gives you again 3528. And then if we are dividing by 60 VB squared, is equal to minus, not minus, it's equal to 58,8, right? But then if you find the square root both sides, because this is VB squared, VB will be equal to square root of 58,8 gives you 7,67. And this is velocity, so it's in meters per second. There you go. That's your final answer for B. A. Now for B, the question says, would a trolley of greater mass have a greater velocity? Let's think about it. Would a trolley of a greater mass have a greater velocity? The thing that's influencing the velocity of the trolley at the end is obviously its mass due to gravity. The heavier it is, the greater the acceleration. It will have a greater velocity because force is directly proportional it will have a greater velocity. Think of it, because the potential energy, not the force here, but the potential energy will be greater. Is that the case? Let's think about it. What will be the acceleration of a greater mass? Still 9,8, but the only thing that's different is the mass. The height will be still the same. So it will have a greater velocity because the potential energy is going to be greater. Okay, so let's move on to the next question. The next question then says, a parachutist of mass 70 kg drops from a plane at 1,200 meters and falls for 1.5 seconds before his parachute opens. He reaches a terminal velocity of 8 meters per second. If he drops, what is his initial velocity? V initial is equal to 0 meters per second, right? What else do we know? 70 kg, it's fine, it's in kilograms, flying at 120 meters and falls for 1.5 seconds before his parachute opens. He reaches a terminal velocity. You must know at this stage what the terminal velocity means. And then the question is saying calculate his kinetic energy after the 1.5 seconds. How are we going to calculate the final velocity in this instance? What do we know that can help us calculate the final velocity? Let's look at this question 2.1. 2.1. What is the final velocity? What information do I have? The information I have is change in t, which is equal to 1.5 seconds. What else do I know? I know V initial is equal to 0 meters per second. Okay, I know acceleration due to gravity is 9.8 meters per second squared. So what am I looking for? I'm looking for final velocity. Okay, very simple. So V final can be calculated using Newton's laws of motion, as well as understanding the equations of motion as V initial plus A times change in t. V initial is 0 plus acceleration due to gravity, which is 9.8. I'm choosing downwards to be positive, not a problem in this question, multiplied by 1.5. In other words, 9.8 multiplied by 1.5 is equal to 13.72 meters per second. That is the velocity of the parachutist, okay, after 1.5 seconds. But the question requires me to calculate the work done, the kinetic energy after 1.5 seconds. I know kinetic energy, EK, is equal to change in kinetic energy is equal to half mv squared. All right, it's about to calculate W net. But anyway, here we're looking at EK is equal to half mv squared at that particular velocity, right? Is kinetic energy after 1.5 seconds. All right? the kinetic energy, half mass, is equivalent to 70 multiplied by that velocity of 13,72 all squared. So a half of 70, I know it's 35 multiplied by 13,72, and this is all squared. My final answer there is 6588,344, but I'll leave it as 34 joules because energy is measured in joules. The next question says, the net work done on the parachutist in slowing him down. What is the net work done on the parachutist in slowing him down? I think I need a bit of space here, so I'm going to take this off and use some of this space from the question we did before to help me answer that question on 2.2. So 2.2 requires me to calculate the net work done in slowing down. All right? So W net, as we know, is calculated by changing EK. Change in EK is half m v squared final minus half m v squared initial, right? So he slows down when he reaches the terminal velocity of 8 meters per second after he opens his chute, right, where his velocity had been 13.72. So the final velocity, half mass of 70 multiplied by 13.72 squared minus half times 70 multiplied by, no, the 8 is the final, so sorry, the 13.2 should be right here, 13.72, sorry, should be right there. Okay, so negative work is done. Why? Because there is a slowing down. So that really makes sense in this instance. Let's do the calculation. Half of 70 is 35, right? Multiplied by 8 squared. 35 times 8 squared is equal to 2,240, 2240, minus 35 multiplied by 13.72 squared is equal to, which I had calculated there already, 6,588,344. Subtracting these two will give me a negative answer to 240 of minus 4,348,34. In other words, it is slowing down. This is work done, and it is in joules. That makes sense pretty much. Let's move on to yet another question and see if we can apply our knowledge at this point in time of what we have learned. Here's a question of a skateboarder, now grade 12. You must not be scared of a question when it presents to you something that you had never seen before. It might be a skateboarder, it might be someone who's ice skating, it might be someone who's driving on a ramp, it might be anything. Your science principles are still applicable. Let's look at this skateboarder of mass 85 kgs practicing a sequence of tricks at the local skate park on a half pipe. The skater leaves a 3.4 meter, a point A, 3.4 meters above the ground. The skateboarder then skates down the ramp towards the point B. He reaches point B, which is 2.6 meters above the ground, with a speed of 3.25 meters per second. Just by rolling along and without using his feet to push himself along the pipe, there is significant friction between the axles and the wheels of the skateboard. It says, state in words, work energy theorem. Okay? So the work energy theorem is what we've been applying all along. Here is the challenge. I want you to try out this question and see if you can come up with the answer. So stating work energy theorem in words is very easy. Don't forget the words, the net or total work done by an object is equal to the change in kinetic energy. All right? 5.2 then says, calculate the work done by the gravitational force on the skateboarder as he moves through the point A to B. Now, if you think of it and you look at this situation, the work done by the gravitational force is done over a distance of, tell me quickly, 1 point, is it 1 point? 3.4 minus 2.6. 3.4 minus 2.6. What do you get from that? Very simple. 3.4 minus 2.6, and you're getting 0.8 meters. That is the change in y, right? And remember that gravity is doing the work horizontally on this particular individual, all right, in the same direction as the movement. It's vertically, not horizontally, but vertically downwards. So work done by gravity in this question 5.1, work done by gravity is equal to the Fg, which is mass times acceleration, multiplied by change in x, multiplied by cos of theta. Okay? Fg being mass of 85 multiplied by 9.8 multiplied by the difference between 3.4 and 2.6, which is 0.8 multiplied by the cos of 0 degrees. Let's do the calculation. My blue baby is close by, and let's find out what the answer is. So 85 times 9.8 times 0.8 times 1 is equal to 666.4. 666.4, and remember we are measuring or calculating the work done in joules. This is 5.2, my apologies, and 5.3 then says, using the work energy theorem, determine the work done by the frictional force. Now, the only force that is opposing the movement of this individual is the frictional force. So according to the work energy theorem, it states that the W net is equal to the change in kinetic energy. So I want you using W net equal to change in EK I want you to then apply your knowledge and calculate for the individual by subtracting work done by friction from work done by gravity and equate it to the change in EK, which is simply found by multiplying half mass velocity final squared minus half mass velocity initial squared. Today, I'm not going to give you the answer for that. I'm going to leave you with a challenge. And I want you to come up with the answer. Just to give you a hint, the answer I got was about 410,09 joules. Let's see if you can come up with that answer. All the best. This is Chow from Chibs.